I am covering what I highlighted for the remote and some of the answers. Let me see if I can get a little bit closer there. Okay, so what is energy? The two key ideas that we're looking at is how are energy, work, and power related. A lot of the kids in class know this. They just aren't familiar with the scientific vocabulary and how science looks at this. Okay, the first thing at Little My Planet Diary talks about wind farms. If you've seen this in the news, especially in Texas, these all froze up and they stopped creating electricity. Of course, in defense of wind farms, they were Texas, so they didn't winterize these. They do have wind farms in Alaska, but they just have antifreeze in them. And that's a step that I don't know whether I would have taken had I lived in Texas, thinking that it's always going to be warm. And if it happens to get cold or snowy, it doesn't last for very long. And how much money would it have taken to winterize these? So depending on where you come down on fossil fuels or green energies, you might not have seen both sides of that story. So that's one of my middle of the road things. Do I like this energy? Absolutely. If I was a politician in Texas, would I have winterized it or would I have saved the money? I can't answer that right now. But anyway, one of the disadvantages is it would only be applicable in places that get a lot of wind. If you've ever driven over Wick Avenue past Ursuline High School toward YSU, you'll see one real big one of these. So we are collecting some of this energy locally as well. So how are energy at work and power related? Not really a fan of this sentence here. It says, recall that work is done when a force moves an object. Now, I didn't find this anywhere else in the book where it was talked about. However, we did talk about the scientific definition of work, that somebody that carries two big heavy boxes of books up a flight of stairs. In science, they actually did more work than perhaps somebody typing a report, because we need a certain amount of force over a distance. And when you think about when you're writing or you're typing a report, you're not really using a whole lot of force. This is a new word here, joules. This is what we measure energy in. So over here, how are power and energy then related? Power is just a rate, and it has an equation that you can use to figure it out. Power means, this says energy transferred, and that's what we learned is work. So I just did something like that. Power equals work divided by time, like how fast you did it. That's the definition of power. One of the examples I gave in class was if I asked you to move 10 boxes upstairs, 10 identical boxes as me, and I did it in a day and you did it over a series of 10 days, some people might say that I did more work because I did it in one day. No, I used more power because the rate at which I did work was a little bit faster, but we did the same amount. We both moved the 10 boxes. So that's where science and kind of just natural human looking at a situation or thinking might be a little bit different. For example, here, you could use an elevator or the stairs to lift the box to the 10th floor. What would have greater power? Obviously the elevator, because it would get done faster. But we might say that, well, we did more work because we carried it up the steps, when in fact we both took the box to the 10th floor. It's so it's an equal amount of work. It's just that how fast you did it. So I get it now. I know that since transfer of energy is work, then power is just how fast or the rate at which I work. So make sure you highlight that information in your book. What are the two types of energy? Oh, I forgot something here. The two basic types of energy are kinetic and potential. Most students remember that. I believe you learned that in 4th grade. It's touched on just a little bit in 5th grade, but I know that we went to full remote last spring, and some teachers didn't go forward, and some assigned the reading, so it might be the first time or the first refresher for you. Kinetic energy means that it is moving. Anything that's moving. And there are 2 factors affecting kinetic energy, and that is both its speed and its mass. The example that I gave in class was if you were a person and you happened to be running across the street, I'm guessing that if you were going to have to face one of these guys down, you probably would choose this guy, because this guy is a little bit smaller. And the speed here is the same. A bigger car, you wouldn't, it would be more difficult. Plus, it's going faster. Both of those things affect how much kinetic energy would be transferred to you. Another example might be, would you want to get hit by a car? But the car's only inching on at about 1 or 2 miles per hour, or somebody on a bicycle that's really cooking, going like 30 meters per second. Which one do you think might hurt you? The car might just push you out of the way, where somebody on a bicycle could really do some damage, because that energy is being transferred to whatever they happen to run into. Okay, so over here it says list the vehicles in order of increasing kinetic energy. So it would be the motorcycle, then the blue car, and then the red car. The motorcycle has less mass. The blue, they're both going the same speed, and the red car tops it out. But when you get out into 8th grade, they might be asking you to solve problems like, would it hurt you more if you were going, if you were going faster and way less, or would you want to weigh more and go slower? So that we're going to be figuring out over here. We can figure that out. This is why they call it physics. We can figure it out with math. But let's answer this question. Describe another example of 2 objects that have different kinetic energies and explain why their kinetic energies are different. Maybe a tennis ball and a bowling ball would have different kinetic energies because they have different masses or weights. Okay, so as I said, if we go over here, here is the formula for finding kinetic energy. In 6th grade, you won't have to memorize this. There is a problem on the review sheet that I will write, I would write it down on there, this particular equation. But let's take a look, and this is my physics here, that I'm taking this, for example, a boy is pulling a 10-kilogram wagon. So that's its mass, so all we got to do is plug it in. And it's a speed of only 1 meter per second. So you take half of his weight, or his mass, which would go from 10 to 5, and then you multiply it by 1 squared, so 5 times 1 would be 5 joules of energy. But let's take a look at this over here. So this is the problem. We took half of his weight, which was 5, and we multiplied it by 1 squared, and we got 1. That means 5 joules. But what if we were to say multiply his mass by 5 times? So let's go down here. Instead of just 10 kilograms, that wagon was 50 kilograms. So just take 50, plug it into the equation. So you're going to have to take half of it, makes it 25, times 1 is 25 joules. Let's go back to that same problem and keep the mass the same, but increase the speed by 5. So we have that 10 kilogram weight plugged into the equation, and now instead of going 1, he's going 5 meters per second squared. So 5 times 5, 5 squared is 25, and look at how much it jumps, 125 joules. So I mean, there's if you increase the speed, it's a lot worse, and that's what I highlighted right here, and that's the question on the review sheet. Changing the speed of a wagon is going to have a greater effect on its kinetic energy. So hopefully if you did this already, if not, I'm going to do it and you could kind of try to do it ahead of me maybe and then check it. So what has a greater effect on an object's kinetic energy? Doubling its mass or doubling its speed? Explain. Obviously doubling its speed. I did not double, I multiplied it, doubling its speed. It really wants you to know that. I highlighted it here. Doubling its speed increases the joules. It would probably double the joules for for the speed. Let's go back and just see. So here, if we doubled it, would be 20. 20 times cut in half is 10. 10 times 1 would be 10 joules. But let's double the speed, which would make it go to 2. So 10 cut in half would be 5, and it would be only 10 joules. Did I say that right? 10 times 5, 10. I think it came out the same, didn't it? All right, okay. Well, I'll do that again, but I want to do this math problem right here. A girl and her dog are running. The dog has a mass of 20 kilograms and the girl has a mass of 60. So don't be afraid of this. Let me zoom in on here. And all we're going to do is remember that kinetic energy equals, I have to take half of the mass and then I have to multiply it by the speed squared. So we have, they're both going 2 meters per second. So that goes here. Whatever 2 squared is, that's 4. And then we have to calculate, let's see, the girl has a mass of 60 and the dog has a mass of 20. So let's do the kinetic energy of the dog would be 1/2 of 20 times 2 squared, which would be 10 times 4, which would be 40 joules. The kinetic energy of the girl would be 1/2 of 60 times 2 squared, which would be 30 times 4, which would be 120 joules. Suppose the dog speeds up and is now running at a speed of 4 meters per second. Calculate the dog's kinetic energy. So now the dog is 1/2. The weight of the dog is 20 times, now the dog is going 4, so it would be 4 squared. So that would be 1/2, which would be 10 times 4 squared is 16, which would be 160. So the dog went from 40 to 160. Are your answers to 1 and 2 reasonably? I would say yes. The girl has more energy because of higher mass, but speed has a greater effect on, I'm just going to do kinetic energy. I'm wondering if it came out the same up here when we doubled it because they're only going 1 meter a second. Let's take a look at that again. So if we're doubling the mass or doubling the speed. Okay, so if we doubled the mass, it would be 20, right? If we cut it in half, it would be 10. 10 times 1 is 10. That's when we did that 10 joules if we doubled the mass. So what if we doubled the speed? The speed would become 2. I think that's the difference there. So this would become 5, and then 5 times 4 would be 20. It wasn't the same, it was 20 joules. So if we doubled the speed, it quadruples the energy. Sorry about that. Okay, so then the two different types of, did I get all of those? Yes, the double potential energies. Potential energies, position or shape of an object. That would be the shape. The gravitational potential is related to its height. And that would just be like this camera right here that you can't see is precariously perched on two boxes and that has the possibility of falling. So we were doing things like if I were to drop this cube on my hand, they didn't really hurt, but the higher that I drop it, the more I can feel it on my hand. So the height really has an effect on that. So it says circle the rock climber with the greatest potential energy and to calculate his potential energy. So obviously it seems like these two weigh or have the same mass, but this guy is considerably higher up in the air. So he would really get hurt a lot. I mean, think about when they fell. So he's 600 newtons times the 4 meters. Why did I use 4 and not 6? Because it says to use the rock climber's lowest foot. So it would be 2,400 joules. So where would the rock climbers at the top need to be to halve their potential energy? So if they're at 4 meters, which is where they are, they would have to be at 2 meters. And then the other type of potential energy is elastic potential, which you know if you've ever trampoline, jumpy house, a rubber band, obviously, ouch, see, it hurt my thumb. So it did definitely have elastic potential energy. Bad rubber band. All right, so just highlight the definition, anything in bold so it jumps out at you, and then answer the questions. Interpret this diagram. Rank the amount of elastic potential energy of the trampoline from greatest to least. So right here is the greatest, and then she's coming up, and then right here she actually has the least elastic potential energy, but probably has greater gravitational potential energy because she's so high up in the air. So obviously that's changing. A ranking of 1 is write your answers in the circles, then explain your answers to the space to the right. And I kind of just did that. So the trampoline is compressed. Or stretched. The most in the middle picture, and the least when she's off in the third, I guess. Okay, identify the object as due to its motion is called, remember, motion is kinetic, stored energy is called potential. What are the 2 factors that affect an object's kinetic energy? How much it weighs and how fast it's going. As you can see, these pictures, think about this question right here. This here is here, we highlighted it here, there's an example here, they spent this whole page explaining it. So I would imagine that that's your clue that there's going to be questions on the test. And if a teacher has it's worth her weight at all, that would be the question that she focuses on, not some little fact that's floating around that they didn't even ask you about. What type of energy does a cup sitting have on a table? I would say gravitational potential, because it has mass or weight and height, or it could fall, I guess you could say. The 2 basic types of energy are potential and kinetic, and any kind of energy that you're talking about, whether it be food, gasoline, wind energy, geothermal, nuclear, they're going to be able to be fit in one of these 2 categories. So thank you, and if you have any questions, email me. Thank you.